So this video has to do with polynomials over a field that have a multiple root, meaning that there is an extension field, E, that contains your field F, such that your polynomial can be expressed in this way. You could write your polynomial as x minus alpha squared, where alpha is an element in E, times some polynomial P with coefficients that could be in the extension field E. Okay, so here is a theorem about multiple roots. The polynomial f of x has a multiple root if and only if f of x and f prime of x share a common divisor of degree bigger than or equal to 1 in f of x. So there's a polynomial with coefficients in the field f, the same as your original polynomial, that divides both the function f and f prime. And this f prime, that's the usual calculus derivative. So this is the derivative from calculus of a polynomial. So let's prove this theorem. So it's an if and only if. Let's start in this direction. Let's assume that my polynomial has a multiple root. So I can take my polynomial and write it as x minus alpha squared times p of alpha, where alpha and p have elements in E. So, where alpha is in E and p is a polynomial with coefficients in E. So I'll take the usual calculus derivative. That can be done using the product rule. So I get 2x minus alpha times p minus x plus x minus alpha squared times p prime of x. So alpha is a root of not only the function f, but also the function f prime. So alpha is a root of both f and f prime. You could see that because plugging in alpha for x here gives me 0. So these are both divisible by the minimal polynomial for alpha over f. The minimal polynomial has to have degree at least 1. So there we go. That proves that f and f prime share a common divisor. So let's go in the other direction. So let's suppose these two functions have a common divisor. So let's say p of x divides both f of x and f prime of x. In that case, any root alpha of the polynomial p of x is also a root of both alpha f and f prime. So alpha is a root of both this function and the derivative. What that means is I could take f of x and write it as x minus alpha times some other polynomial q of x. Taking the derivative, again using the product rule, I get q of x plus x minus alpha q prime of x. So alpha is a root of f, and alpha is a root of f prime. So if I look at plugging in or evaluating this polynomial at alpha, I should get 0. 0 should be q of alpha plus 0. So I took this derivative and evaluated at alpha. Alpha is a root, so this is 0. This term is 0. So therefore, alpha is a root of q. So alpha is a root of q, and that proves the statement, because then my function f is equal to x minus alpha, and then I'm going to take q and divide by another x minus alpha and write it as some other term, r of x. There. Now I have a multiple root. Okay, this is a nice theorem because it holds for an arbitrary field f, not just the reals or not just fields with characteristic 0. So we're going to use this theorem in our final topic of the course, finite fields. All right, I'll see you there.